How can we use this information about core electrons and valence electrons to write shorter electron configurations? I don't know about you, but when I write those big long electron configurations, they get really long and cumbersome, and I would love to have a shortcut. So we're about to learn a shortcut. This shortcut is called shorthand notation or noble gas configuration. And what we're going to do is we're going to replace all the early terms before the first valence electrons. We're going to replace them with the appropriate noble gas element. So this is going to take less space than the longhand electron configuration, which is great. So let's use this selenium example again. Here, we've got these 34 electrons, and my valence electrons start here. That's my first valence electron there with the 4s2. So what I want to do is I want to not have to write any of these starting terms in my electron configuration. So I'm going to replace them with the correct noble gas that ends 3p6. That noble gas is argon. So I write the element symbol for argon in square brackets, and then I write the rest of the electron configuration. Notice that the rest of the electron configuration is exactly the same as how I wrote it before. This part has not changed. It's still in that same order we've been using, whether you use the diagonal rule or the reading the periodic table method. All we did was replace these early elements with a noble gas. So, what's the step-by-step procedure for doing this shorthand notation? Here I'm showing you where the noble gas configuration comes from, but it doesn't save you time or effort if you have to write the whole electron configuration to begin with. So, how can we take the shortcut? We have to find the correct noble gas element symbol and write it in square brackets. How do you find the correct noble gas element symbol? You start at your target element, you go up one period, and then you go all the way over to the right until you get to the noble gas column. Then, step 2, you write all the remaining electrons between that noble gas and your target element. This is going to include all the valence electrons. It may also include some F electrons and D electrons from lower energy levels. You'll need to read the periodic table or know your diagonal rule to make sure that you cover all of those D and F electrons. An important tip to help you do that is to remember that after your noble gas, the first term you write is always going to be an S sublevel in the energy level that matches the period of the target element. The terms you write after the noble gas are the same and in the same order as the longhand notation. So that's what I showed you with selenium, is that the ending for the electron configuration looks exactly the same. It's just the beginning that changes. We replace the starting terms with a noble gas. Another trick you can do, if you subtract the atomic number for the noble gas from the atomic number of your target element, that tells you how many electrons need to be placed after the noble gas. So that way you can make sure you haven't accidentally skipped any D or F electrons. So let's look at this. Let's do sulfur. Sulfur's here on the periodic table. Step 1 is to find the correct noble gas. If we go up one period and all the way over to the right, the noble gas here is neon. So we write capital N lowercase e in square brackets. And then we start filling in the rest of the electron configuration that comes after neon. So we start here in period 3. There are 2 electrons in the 3s sublevel. Then we move over to the 3p sublevel, and there are 1, 2, 3, 4. Sulfur is the 4th element in the in this 3p sublevel. Therefore, we have 4 electrons in the 3p sublevel. Now, just as a double check, neon has 10 electrons and sulfur has 16. Therefore, I should have 16 minus 10 is 6 electrons. I should have 6 electrons in this electron configuration, and I do. And in fact, because those are all s and p electrons, that's the number of valence electrons that I have. There are no d or f sublevels here to worry about, so just that 2 plus 4 is 6 valence electrons. So you can see that this noble gas configuration is really helpful for spotting these valence electrons because you don't have this huge electron configuration. You're trying to sort through which electrons are valence. It's just a lot easier to read with the shorthand notation. Let's do a little bit more complicated one. Let's do germanium. Germanium is here on the periodic table. If we go up 1 period and over to the right, our noble gas is argon. So we write the symbol for argon in square brackets, and then we start filling in the electron configuration after that. The next is the 4s2, then the 3d10. Remember to subtract 1 from the period to get that energy level, the 3d. And then we are 2 elements into this 4p block here, so it's 4p2. And in terms of our valence electrons, we count these 2 electrons, we count these 2 electrons. We do not count these 10 electrons because they're not in the highest energy level. They're in energy level 3, not energy level 4. Only count the electrons that are in the highest energy level. So here are some more practice problems for you to try. So now you can check your answers. And if we want to do kind of a tally of how many valence electrons each of these elements have, here we have 7 valence electrons. Here we just have 1 valence electron. Here we have 2 plus 6 is 8 valence electrons. We don't count the D. And here we have 2 plus 3 is 5 valence electrons. We don't count the F or the D sublevels. I hope this helps.